Hello, welcome, Calculus 2. So I am your professor, Jeremiah Dyke. So normally, in Calculus 1, if you were to have had me as a previous student, we would have covered all material from the preliminaries, Chapter 1, all the way to the end of Chapter 5. However, given some of the scheduling conflicts and given some of the things that we've had to endure with the crisis, I'm going to begin Calculus 2 towards the middle of Chapter 5. So we're going to begin at Chapter 5, Section 3, which I'll talk about in just a little bit. I will tell you, so for Calculus 2, the way this works is, for this class, we're going to cover material from Section 5.3 all the way to Chapter 10, and I believe it's Section 5 or 6. So this is a lot of material, right? We're going to span quite a breadth of mathematics here. I'll say a few things about what resources you have available to you in just a second. I do want to give you a quick roadmap of where you are and where you may have to go from here. So right now you are in Calc 2, which is Math 264. So depending on your major, and we can chat about that later, depending on your major, if you are in, say, engineering, hopefully at this current semester, while you're taking Calculus 2 with me, you are also taking linear algebra. I'm just going to abbreviate that. So linear algebra, which is, I believe, Math 266, if I'm not mistaken. But you should, if you're planning on majoring in engineering, the majority of the four-year schools in the state of Virginia would like you to take linear algebra as well as Calc 2. And since we offer them both every spring semester, you should be taking both linear algebra and Calculus 2 this semester. If you're only taking Calculus 2, that's not a problem. It's not a huge problem. You can take linear algebra again next spring. Just a lot of students like to take them at the same time and kind of get a lot of their hardcore math credits out of the way. After those two classes, you can take Calculus 3, which I'll be teaching next fall, and then you can take differential equations, which again I teach every spring. So either you will be taking Calc 2 and linear algebra this spring, or you'll be taking linear algebra and differential equations next spring. That's all assuming that you are planning on doing some type of engineering field. Now, back to Calculus 2. So I believe if you ask any student, they will tell you that Calculus 2 was probably the hardest of the calc sequence. Calculus 2 is much harder than Calculus 1, and I would argue, and most would agree, that it's actually a lot harder than Calculus 3 as well. It is a demanding course. Now, resources, in terms of resources. So we offer, as a Lord Fairfax student, we offer free tutoring. Just reach out to me. You have, obviously, my office hours, which are in the syllabus. I also want to direct you to my website, which I'm going to show you right now. So this is just, if you notice at the top, just my first name, last name.com, jeremiahdyke.com. From here, you can click courses. Here's the various courses that I teach. If you click on Calculus 2, what you'll find there is the handouts that I'm going to be using during these lecture videos that I'm presenting to you. So if you were to make your way there and say print off some of these handouts, you then could watch the video, and you would have you wouldn't have to pause as much and write as many notes, because you would have all the handouts with the questions right there, and you can just write on that paper. So all that to say, this is a somewhat demanding class. You are going to need to find a way to practice this material. How do I put it? There is college is full of a lot of almost engineers, right? I was an engineer major until, right? I mean, just to give you a factual statement. So I've been teaching full-time here at Lord Fairfax for, I've been teaching post-secondary here, George Mason, etc., probably almost 10 years. And it goes something like this. Calculus 1, there's probably 35 students in Calc 1. By the time we get to Calc 2, there's probably maybe 25. By the time you get to Calc 3, maybe 15. This is year after year after year. I tell the same story. I tell the same students that you do need to study. It's not impressive that you were good at math in high school. It really wasn't, because you're in a class where everyone was good at math in high school. And if you're not careful, you can find yourself in a position where you just can't make it, and it's a shame. So find ways to practice. I will post a whole bunch of homework problems they're not graded, but they're just to give you an idea of what to expect on the test. That'll all be in Canvas, as you'll be able to find those practice problems. If you don't have the textbook, no problem, reach out to me. There's lots of free resources out there, but just like you wouldn't, I mean, listen to me. I know you're probably daydreaming already, but listen, you would not watch somebody play the piano on YouTube for 2 hours and then go to a concert and play for others, right? I mean, at some point in time, you would sit down and start playing the piano yourself. And it's the same way in math. You can't watch someone do math, right? And then expect that will translate to your abilities on tests, because math is a contact sport. You got to roll your sleeves up. You got to get in there, make a bunch of mistakes, figure out what you did wrong, so you don't make those mistakes on the tests. And so you have to get the reps in. And the only way to do that is to find exposure, to get some practice problems. All right. You got this. Let's jump right in. So, as I said, we're going to kind of start in Chapter 5, Section 3, and what we're going to discuss for this section is the derivatives of inverse functions. So let's take a step back, right? So an inverse function, right? I mean, obviously, if we wanted to be able to do calculus with inverse functions, it would be nice to know first, what is an inverse function? Let's make sure we really understand what we're talking about. So let me kind of draw your attention down here. All right, so here is a function. Right, f of x is equal to x plus 3. Now, notice here I have two sets, set A, set B. You and I also notice that the only numbers that exist in set A, the number 1, 2, 3, and 4, right? There's the only 4 numbers that exist in that set is 1, 2, 3, 4. Now, what's going to happen is we are going to, just like you plug 1 in for x, right? This is just a more, it's just a different way of thinking about what it is that you're doing. So when someone says f of 1, right? You and I already know. We're going to take 1, we're going to plug it in for x, and we have 1 plus 3 is 4. We know f of 1 is equal to 4. I'm trying to give you a way of visualizing this through set theory, right? So here's the number 1, and let's say in this other set, this is the number 4. And what you have is you have the number 1 mapping, right, to the number 4. Now, it's not possible for 1s to turn into 4s, right, unless they undergo some type of transformation. Now, the function is the transformation. So this right here is the function. I'll just write it as f so I don't confuse you. So 1 undergoes a transformation, that's her function, and what comes back out is 4. Same way, right? So 2 maps to 5, 3 maps to 6, 4 maps to 7. We got the idea. Now, this is just a typical function, but now the topic under consideration is that of an inverse function. So the idea is, so if this is your domain and this is your range, right? You plug in a 1, you get back out a 4. Let's now think of what if we wanted to go back, right? Because if you want to be able to start with 4 and get back to 1, now you're talking about an inverse. So look, in mathematics, I am not interested in addition unless I have subtraction, right? I'm not interested in this idea, this operator of multiplication, unless I have division and so forth, because I want a way to undo what I just did. And that's what we mean by an inverse function, right? So one that's going to undo the previous transformation. All right. So that gives you just a decent overview of what it is that we mean by inverse function. Now, a more formal definition of inverse function is here. So notice, let me come down here. So the way we denote inverse, it is I'll be honest with you, it's one of the sloppiest notations in all of mathematics, right? I mean, you don't know how many students over the years I've had think that this is an exponent. They think that this is f raised to the power of -1, right? But no, this literally is the notation for the inverse of f. The inverse of f. Now, so what are we gonna go from here? So I need to stay in pre-calc for a little bit, because I want to not only do I want to I'm going to ask questions like how do you know if two functions are inverses? I need to ask questions like how do you find an inverse of a function? And then I need to discuss some of the implications, the geometric implications of inverses. And then finally we can start talking about calculus of inverse functions. So look, I chose something very easy. So if your original function is just x plus 3, right? I have not given you a strategy for how to find inverses, but how would you undo x plus 3, right? In other words, how would you go from 4 back to 1? Well, don't you just agree with me that it's going to be x minus 3? So x minus 3 is the inverse of x plus 3. Okay. Now, let me show you what this formal definition is trying to say here. Notice the formal definition is saying, okay, look, if you have two functions, right? So I have, this is f inverse. If you wanted to show that these are indeed inverses, you can form a composite, right? F of g of x, or g of f of x. Now, so if I were to form a composite, what I'm going to do is go ahead and write both of these functions beside each other. And if you don't mind, although this is the notation for inverse, I'm just going to go ahead and call it g for right now. That way it mirrors, right? F and G mirrors what our definition is saying up here. So let's just assume for a second that I gave you these two functions, right? And I said, hey, are these inverses? Right? Are these inverse functions? Well, you may be savvy. You may just notice right away that yes, they are inverse functions. But here's a quick way that you could tell. Well, look what happens if you form a composite, f of g of x. So in this case, we are taking g of x, right? We're taking g of x and we are plugging it in for f, right? Into f. So what would that look like? So we would now have, instead of x plus 3, we would be taking g of x, plugging it in for x. And now, if we drop these parentheses, what do we get? Right? So we have 3 minus 3, cancels out, so you're just left with x. You would get the same thing if you were to take g of f of x. And that's exactly what it's saying here. That you know two functions are inverses, right? You know they're inverses. If one goes to 4s and 4 can go back to 1, you know that they undo each other when you form a composite and all that is left is x. Okay. So let's try it, right? So notice the first example. I give you f, I give you g, and you're asked to show that the functions are inverse functions of each other, right? So how do we show that f and g are indeed inverses? Well, we're going to go ahead and we're going to do exactly what we did on the previous page. We're going to form a composite, f of g of x. So let's see what this looks like. So f of g of x. So let's start with f. So here is 2x cubed minus 1. This is f. And I'm going to go ahead and write g just so it's all right beside each other. G of x is simply the cube root of x plus 1 over 2. All right, so the first composite was we're going to f of g of x. So we're going to take this g and we're going to sub it in for x in f. Let's do that right now. So what does that look like? So here is where an x would be, x to the power of 3 minus 1. Let's go ahead and substitute. All right, so now we got the cube root of x plus 1 over 2. All right. So at this stage we have formed the composite, and let's simplify it and see what's left. So look, if you cube a cube root, well, doesn't that make sense? That would undo. It's like, okay, 3 to the power of 2 is 9, right? And the square root of 9 is 3. So 3 squared is 9, square root of 9 is 3. So you see how they undo each other, right? So the cube, if you cube a cube root, those operations would cancel. You would be left with 2 times just the radicand, x plus 1 over 2, minus 1. All right, well, these 2's would cancel. You will be left with x plus 1 minus 1. And obviously, if you have 1 and you take 1 away, you're left with just x. And you can see that this meets the criteria that f, the composite of these two functions, is indeed x. Now, we can get lost in a lot of these math formulas and stuff, but let me, if you don't mind, if you have the energy, right? Hopefully you've had a cup of coffee or an energy drink or something. Come follow me for a second. Ready? So let's take a look at this function. If I give you a value of x, what's the first thing you would do, right? So if I said x is 1, tell me think about it. Obviously you can't tell me, right? Because you're on the other end of a computer or screen. But if we could see each other and I said, look, if x equals 1 and I plug 1 in here, what is the first thing I would do? Well, what are my choices? Well, I can subtract 1. That's one operation. I can double it, multiply by 2, or I can raise it to the power of 3. Don't you agree with me that the first thing you would do is raise 1 to the power of 3? So the first thing you would do here is cube it. What's the last thing you would do if I gave you x is 1 here? Right? Well, the first step you would do is cube here. Do you agree with me? The last step you would do here is the cube root. Interesting. Okay. So you can, what would be and I can show you here, what's the last step that you would, operation-wise, that you would do for f? Well, if I gave you x is 1 to the power of 3 is just 1. The second operation would be times 2, and the last operation would be to subtract 1. Do you agree with me? The last operation you would do is subtract 1. And what's the first operation you would do here? You would add 1. So do you see how the last thing you do here is minus 1? First thing you do here is plus 1. Do you see how these are indeed inverse operations? They are undoing each other. So I will spare us from going through g of f of x, but you could try it on your own. Just plugging 2x cubed minus 1 in here for x. Again, you will just get x. They are indeed inverse functions. Okay, so I want to talk a little bit about some of the geometric implications of inverse functions. So, but to make sense of this, I want to start with two tests that you have seen and heard of before. So let's start with the vertical line test. Right, so recall that the vertical line test was a quick geometric test to be able to state whether the graph is the graph of a function, right? So in this example, if I were to draw a vertical line, see how this vertical line touches our graph in 2 locations. Same vertical line touches our graph at 2 locations. So we would make the statement that this fails the vertical line test. And that is basically saying that this graph is not the graph of a function. Now, again, so since this is not algebra 1, let's try to make sense of this. So if you look at your graph, so notice that you have your x input, right, is z, and then your y inputs or outputs are a and b. So if you were to identify this point, so this first point is located at z and then a, and this second point would be located at z and then b. So what's happening here is that you have an input of z, and that same input is mapping to 2 different outputs. That would be like if you put some change into a soda machine and hit Coca-Cola, and then you could get Coca-Cola or you could get Mountain Dew, right? Do you understand? Like, there's something wrong. Like, you're hitting the Coca-Cola button, you're just not getting Coca-Cola back out, right? You could be getting Mountain Dew. So this input-output relationship is failing to meet the requirements to be called a function. Now that's a vertical line test. Now notice that there's also a horizontal line test. And before I tell you what the horizontal line test tells us, let's make sure we understand it. So just like before, if I were to draw a horizontal line, notice that this one horizontal line makes contact with the graph in two locations. So we would say that this fails, right? This graph fails the horizontal line test. And again, in terms of mapping, so in this case, we have A, right? A maps to Z, and B also maps to Z. So what information does a horizontal line test tell you? Well, a horizontal line test will tell you if your function has an inverse. I'll say that again. So this graph fails the horizontal line test. So this graph does not have an inverse. Now, in formal language, we normally use terminology one-to-one. Right? So meaning a one-to-one correspondence, which is, so the idea is that if your function, if it is one-to-one, then it has an inverse. If it passes the horizontal line test, then it is one-to-one. Okay, now all of that finally gets us to the geometric implications. So if you take, and you can try this, like if you go back, my apologies for scrolling back, if you go back to these, remember how we showed that these two were inverses? If you take those two and graph them on your calculator or Desmos, or you take these two functions and you graph them on your calculator or Desmos, either way, you're going to see, because they're inverses, you are going to see a symmetry. The graphs are symmetric about the line y equals x, right? So notice how you have point AB here, and then you have point BA here. So notice how the input is the output. The input of one graph is the output of the other graph. The domain is the range. The range is the domain. Now, let me, now that we've kind of almost finished up our pre-calculus, let's go over a fairly important theorem, right? So the existence of an inverse function. So there's two parts to this theorem. So the first part says, look, if a function has an inverse function, right? So if there is an inverse function, it's only going to have an inverse function if and only if it is one-to-one, right? Back to that horizontal line test. It's got to pass the horizontal line test for there to be an inverse. Now, the next part of the theorem says, if your function is strictly monotonic, now, monotonic means it's either everywhere increasing or everywhere decreasing. Okay? So like this is not monotonic because it's increasing and then it starts to decrease, then it starts to increase. This is not monotonic. But notice that this graph is monotonic because it's always increasing. Okay? So this theorem says if your function is strictly monotonic over its entire domain, then it is one-to-one. Now we already know if it is one-to-one, then it has an inverse function. So here's an example. So if you wanted to to show, so notice, so we'll start with A. So if you wanted to show that this function has an inverse, right? In other words, maybe you're not asking what is the inverse. That's not your question. Your question is, how do you show that it must have an inverse? Well, let's see if we can use this theorem 5.7 to our advantage, right? Now, do you remember back in Calc 1, do you remember the first derivative test, right? Do you recall that f prime of x, the first derivative, I don't know, maybe it's been a while, right? Maybe you've been just playing video games, right? Just all-nighters over the last 4 weeks. You've forgotten everything you learned in Calc 1. Hold on. So come with me. Look, this is a derivative, okay? So you remember that, right? You remember that word in Calc 1? That's a start. So this is a derivative, right? So a derivative is a function, right? The derivative, you have to give it some information in order to get back some information. Now, regular functions, right? Regular f of x, if you give a regular function an x value, it will give you back out a y value, right? Now, for a derivative, if you give it an x value, what does it give you back out? Right? It gives you back out the slope, right? More importantly, the slope of a tangent line at a point on a curve. Okay, so the first derivative tells us slopes. Now look, what does a slope mean? Well, don't you agree with me? If your slope is 3, then you're increasing, right? If your slope is -3, you're decreasing. If your slope is 0, then you are constant, right? You're not increasing or decreasing. So what I'm going to do is I'm going to take the derivative of this first function. We're just going to eyeball that. All right, so if I take the derivative, so f prime, it's an easy derivative to take. All right, so that's going to be 3x squared plus 1. Now, if I were able to see you, if we had a classroom to discuss these ideas, then I would open the floor and ask, how does this alone tell you that this function has an inverse? What is it about this derivative that leads us to be assured that this function, original function, does have an inverse? Well, let me pose the question in a different way. Is there a way for you to get a negative number from this function? Right? Think about it. I mean, if you let x equal 1, you'll get out a positive number. What if you let x equal -1? Would you get out a positive number or a negative number? Well, of course, right? I mean, no matter what negative number you give it, you're going to square. So, and if you, a negative multiplied by a negative is a positive. So, no matter what input you give this, you're always going to get positive numbers. Always are going to be positive slopes. Well, if you only have positive slopes, then this function here is always increasing. This is monotonic. Now, at some point in time, you should stop listening to people with red pencils, pens, and markers, and you should, give it a shot. Try it on your own. You could go to Desmos. You can go to Desmos right now and graph this function. And what I'm telling you is it will always be increasing. So if it's always increasing, then it's monotonic. If it's monotonic, then it's 1-to-1. If it's 1-to-1, it has an inverse. See how we did that? So this function here, you could try the same test, right? You would take the derivative. This time it would be 3x squared minus 1. And this is a problem, right? Well, it's not really a problem. It's just, it is not monotonic, right? Because let's think about it. From this derivative here, depending on the x value, you could get positives or negatives, right? I mean, think about it. What if x is 0? If x equals 0, then your slope is a negative number. But if x is 2, then your slope is 11, right? So you see how if you have negative slopes and positive slopes, then your graph is going up and down. If it's increasing, decreasing, then it's not monotonic. So let me now show you a. I mean, this is a great technique, but what you're going to find is that this is sometimes a lot easier said than done, right? So if you want to find the inverse function, so for this example, you have f. What you don't have is f inverse. So I'm going to try to capture these guidelines above. I'm going to try to use some, in other word, less formal language. But I will keep with the steps just to make things easy. So if you and I were in pre-calc 1 right now, and I were trying to teach you how to find an inverse, here's exactly the way I would explain this to you in pre-calculus. I would tell you to replace that f of x notation with y. Okay, so that's easy. So that just, instead of saying f of x equals, we're just going to say y equals the square root of 2x minus 3. Okay? That's step 1. That's easy enough. Step 2 is easy as well. In essence, you're gonna swap the x and the y, right? You're gonna swap places. So the x goes where the y goes where the x is. So swap x with y. Okay. And the only time you have to roll your sleeves up at all is step 3, where now you have to solve for y. Okay, so let's solve for y. So easy enough. If you want to, first thing we got to do is get rid of this square root. So we're going to square both sides. So that would leave me with x squared is equal to 2y minus 3, right? I mean, literally, I just squared this side, squared this side. Okay. Y is still not by itself, so let's go ahead and get that 3 to the left side. So I got to do the opposite of minus 3, so I got to add 3. And last step, let's just divide both sides by 2. So I got x squared plus 3 over 2 is equal to y. Now, the last step, although it's just notational, it is important. So, if your customer needs to know what you're trying to do here, right? So the customer has no idea what y is supposed to represent here. So we don't want to be sloppy. So we want to replace the y, now not with f, because this is not f. This is now, so y with f inverse. All right, so let's get rid of this notation, and you want to write your inverse notation. Okay, so those 4 steps, all right, those 4 steps is the way that you would find the inverse. Now, let's assume that you were, that this question was, I don't know, somehow it was either test related, but in other words, it's one where you really want to be sure that you did it correctly. right? You don't want to have any points taken off for any silly mistakes. So do you realize that here is your proposed inverse, and here is the original function? Do you remember the very first thing I told you that you could do? You could take inverse functions, right? If you really wanted to double check your work, you would just take the composite of f of g, and you would make sure that you get x. And now you would be positive that you have inverse functions. Okay, so I think it's about time for a break. I appreciate your patience. I know this is going to be hard getting back into the swing of things, but no worries. So when we get back, we'll go ahead and finish up this section, and we'll talk about the calculus of these inverse functions. I'll see you there.